Hello and welcome back to the Explainer. Today we are diving deep into a molecule that is, well, pretty much everywhere, from the farms that grow our food to the cleaning supplies under your sink. It's a compound that's pungent, it's powerful, and it's absolutely pivotal to our modern world. We are talking about ammonia.
You know that sharp, really distinct smell you get from some window cleaners? Or when you think about the massive, sprawling fields of crops that have to feed billions of people? Well, the hidden hero behind both of those things is the exact same simple but totally fascinating molecule, ammonia. It's a real chemical superstar, and in the next few minutes, we're going to break down exactly what it is, how we make it, and why it is just so incredibly important. So here's our game plan for today. We'll kick things off by properly meeting the molecule. Then we'll see how it's cooked up in a lab versus on a massive industrial scale. After that, we'll explore its unique properties, figure out its crucial uses, and then we'll wrap it all up with a quick quiz to make sure all this knowledge sticks. Sound good? Let's get started.
All right, first things first. Let's get properly introduced to our molecule of the hour, ammonia, or as you'll see it written in chemistry, NH3.
So what exactly is ammonia? Well, at its core, it's a pretty simple compound. It's just one nitrogen atom bonded to 3 hydrogen atoms, which gives it a molecular mass of 17. But the really interesting part, the thing that gives it its unique chemical personality, is its lone pair of electrons. You can think of this as ammonia's secret power. This unbonded pair is what makes ammonia basic, and it's the key to so many of its reactions. Trust me, we'll be coming back to this idea.
So how do you actually make this stuff? Let's start small scale, like we're in a high school chemistry lab. Making ammonia in the lab is a pretty straightforward 4-step process. First, you mix together 2 solids, ammonium chloride and calcium hydroxide. Second, you gently heat that mixture up. That gets the reaction going and starts producing ammonia gas. Third, the gas that comes off is a little wet, so you have to dry it. You do that by passing it through a substance called quicklime. And finally, you collect your pure, dry ammonia gas. But hang on a second. That third step is really important. Why must we use quicklime? I mean, chemists have lots of things to dry gases with, like concentrated sulfuric acid or calcium chloride. So why are those a total no-go when it comes to ammonia? This is a classic exam question, so you'll want to pay close attention here. And this table shows you exactly why. Remember that lone pair of electrons we talked about, its secret power? Well, that makes ammonia a basic or alkaline gas. Sulfuric acid and phosphorus pentoxide are both acidic, so if you try to use them, they would just react with your ammonia instead of drying it. You'd lose your entire product. Calcium chloride also reacts with it, forming a whole new compound. The key takeaway is this. Quicklime works because it's also a basic compound, so it happily grabs the water and leaves the ammonia alone. It's all about chemical compatibility.
Okay, so making a little bit of ammonia in the lab is one thing. But to make enough fertilizer to feed billions of people, yeah, we need to produce it on a truly massive industrial scale. And that brings us to one of the most important chemical processes ever invented, the Haber-Bosch process. Getting this process right is like following a very precise recipe. You start with your reactants, nitrogen gas, which we get from the air, and hydrogen gas. You mix them in a super strict ratio of 1 volume of nitrogen to 3 volumes of hydrogen. Then you put this mix under some extreme conditions, a temperature somewhere between 450 and 500 degrees Celsius, and a crushing pressure of over 200 atmospheres. And to make it all happen faster, you use a catalyst of finely divided iron, which gets a little help from a promoter, molybdenum. But why these exact conditions? Well, it's a brilliant chemical balancing act. The reaction to make ammonia actually gives off heat. Now that means a lower temperature would technically give you a better yield of ammonia. The problem? At low temperatures, the reaction is just painfully slow. So 450-500 degrees is the perfect compromise. It's hot enough to go fast, but not so hot that you destroy your yield. The super high pressure? That's there to literally squeeze the nitrogen and hydrogen molecules together to form ammonia. And the catalyst is like a chemical matchmaker, just speeding up the whole process. So now we know how to make ammonia, both big and small. But let's get to know its personality a bit better. What are its defining characteristics? Let's start with one of its most famous traits, ammonia and water. They have a very close relationship. How close are we talking? A mind-boggling 702 times. No, that is not a typo. It's incredible. At standard temperature and pressure,
About 702 volumes of ammonia gas can dissolve into a single volume of water. It's so ridiculously soluble that it directly explains something we saw back in the lab prep. You can't possibly collect ammonia over water, because the moment it touches the water, it just dissolves instantly.
Now, besides its extreme love for water, ammonia has a few other key traits to remember. It has that really strong, pungent smell. You know the one. It's alkaline, which you can easily prove by watching it turn a piece of moist red litmus paper blue. It is also less dense than air, and that is why in the lab we collect it by pushing the heavier air downwards and out of the way. And finally, while it isn't technically poisonous, you definitely do not want to be inhaling big lungfuls of it.
So we've covered what it is, how to make it, and what it's like. But why do we go to all this trouble? Why does this one little molecule matter so much? Okay, this is the really crucial part. Without ammonia, our world would look completely, totally different. Its number one most important use is in making nitrogenous fertilizers. These are absolutely essential for modern agriculture. It's also a key ingredient for making explosives like ammonium nitrate. It serves as an eco-friendly refrigerant in big industrial ice plants and cooling systems. And of course, it's used in all sorts of household cleaners because it is fantastic at dissolving grease and grime. It is a true workhorse of the chemical industry.
Okay, you have taken in a whole lot of information. So let's do a quick fire round, just to see what's stuck with you. Ready?
First question for you. In the Haber's process, what is that all-important ratio of nitrogen to hydrogen? I'll give you a second. If you said 1 volume of nitrogen to 3 volumes of hydrogen, you are absolutely correct. Question number 2. Think back to the lab prep. What is it about ammonia that allows us to collect it using downward displacement of air? It's because ammonia is lighter or less dense than air. Nice and simple. And for the final question, let's circle all the way back to the beginning. Why is ammonia considered a basic gas? What's its secret? It is that lone pair of electrons on the nitrogen atom. That's what gives it its power. Fantastic job. And that wraps up our explainer on the amazing molecule ammonia. If you found this helpful, please go ahead and like, share, and subscribe, and definitely don't forget to press that bell icon. Thanks for watching, and we'll see you in the next one.